Alright, let's review some of the things that we have learned, and let's begin with an example that illustrates again a production function. So specifically we see here a production function that converts labor into output Q, and the function is 3 times labor squared minus 0.2 labor cubed. And the function is basically defined for a maximum amount of labor of 10, and we assume that labor is perfectly divisible, so workers can work the entire day or half a day or just a couple of hours. So let's first draw it, and we want to put labor on the x-axis, and you can see I have activated my keystroke so that you can see what I do in Excel. So now first thing we do is we create a column that starts at 0 and goes down to 10. So I highlight everything, and then I go to Home, Edit, Fill, Series, and I fill a series with a step value of 0.1, and it ends at 10. So that's labor. I can spell it out. Labor, and then output Q. Output. So the formula is equals to 3 times labor, which we pick up from here, squared, minus 0.2 times labor raised to the 3 cubed. And now we can copy down that formula. You can copy down with Control D. And let's take a look at what that curve looks like. So let's insert recommended chart. And then let's take this one. So you can see we have here a typical S-shaped production function, but let's make it a little bit nicer. So let's format the axis, make sure that everything is on tick marks. Let's split out the tick marks and also the labels. I gotta get out of the way here. Okay, so now it looks a little bit more organized. And well, since the maximum is 100, let's just limit it to 100. And we can also add vertical grid lines. Okay, so now it looks really nice. So that is our total production function, and you can see it's nicely S-shaped. Actually, I want to make it a little bit bigger. Make it really big. Okay. Okay, so this is what we have. So the first question is, what is the average labor product? Well, the average labor product is dividing total output by labor. So ALP, average labor product, is equal to the total output divided by labor. Of course, we get now an error because we cannot divide by 0, but we still can copy down that formula. And then in Excel, whenever you have something like an error, like divide by 0, let's just replace it by number not available. Okay, so the average labor product, we have defined it in Excel, but of course the average labor product is total output Q over L, so that would be 3L divided by labor, and the square becomes 1 minus 0.2 L squared. So that seems to be A. Okay, what is the marginal product of labor? The marginal product is the slope at any point, and so you can see that the slope is initially really flat, and then it gets steeper and steeper at any point, and somewhere there is like a point of inflection, and then the slope becomes again flatter and flatter and flatter. But mathematically, the slope is the first derivative. So the marginal labor product, or the marginal product of labor, MLP, is the first derivative, dq, with respect to dl. So we get 6 labor minus 0.6 times L squared. Okay, let's also add that. Marginal labor product. That is equal to 6 times L minus 0.6 times L squared. Okay, so there's a typo somewhere. Oh, of course I cannot type L squared. I have to pick it up from here. Okay, so we can copy this down. And so the right answer here is 6L minus 0.6 L squared, so that looks like C. Okay, so now let's draw the marginal and the average labor product. So for this purpose, we first highlight the first column that will go to the x-axis. Press Shift, click with the mouse, ALP and MLP. And now let's take a look at the average labor product and the marginal labor product. Insert recommended charts. And we take this one. Yeah, that looks pretty familiar. What we have seen in the previous video. We don't need actually. Okay, let's also format that a little bit nicer, just like the other one. So format axis on tick marks. Let's spread that out a little bit. Also the labels. 10. And we add again the vertical grid line. Chart title, grid line, vertical. Okay. Okay, so now the next question is, at what labor input is the average labor product maximized? Okay, it looks like here. And when we hover with our mouse, it looks like 7.5. So mathematically, however, we will find the point of the average labor product where the slope is 0. That will be a maximum. So what we do is we take the derivative of the average labor product function, d average labor product with respect to L, which is this term here, and that is 3 minus 0.4 L, and it has to be equal to 0 because we are looking for a maximum where the slope is 0. And then we can rearrange terms and we get 0.4 L equals 3, and if we divide 3 by 0.4, we get L star equals 7.5, which is what we had here too. So at the labor input of 7.5, we have the maximum average labor product. So, and now the next question is, what is the maximum labor output? So now we have to look up the value on the y-axis. Well, there are two ways of doing it. We can go to 7.5 and look it up here, but let me first freeze the top row. So view, freeze, top row. So then whenever we scroll down, we still can see, okay, 7.5, so the value is 11.25. So, but of course what you could also have been doing is just plug in 7.5 into the first formula. I just do that quickly here in Excel, and then you could also have said, okay, this is equal to 3 times 7.5 minus 0.2 times 7.5 squared, get 11.25. What is the marginal labor product where the average labor product is maximized? Okay, so now we know that wherever the average labor product is maximized, it intersects with the marginal labor product. So the marginal labor product where the average labor product is maximized, but that's also the 11.25 that we just have calculated. But if you're not sure, you could have also plugged in the 7.5 into the marginal labor product function. I'll just do that quickly here. Then you would have said this is equal to 6 times 7.5 minus 0.6 times 7.5 squared. And you see you also get 11.25. At what labor input is the marginal product of labor maximized? So that requires to find the maximum here, and it looks like as if it's 5. As we hover over with our mouse, it looks like 5. And the value is 15, but let's double check. So we take the derivative of output with respect to labor. I mean, that's the marginal product of labor. So we take the derivative of the marginal product of labor with respect to labor, and then set that equal to 0. So the marginal labor product is 6L minus 0.6. Okay, so let's do it here. So the derivative of the marginal labor product, where it has its maximum, so that is 6 minus 0.2 times L, and that has to be again equal to 0. So now we can rearrange terms, and we get 1.2 L equals 6, and then L is equal to 5, which is what we can see here as well. Okay, so then that. And it looks like that the marginal labor product at 5 is exactly 15. But it's not a question, so we didn't ask for that one. Okay, so now let's move to cost. So here we looked at production. We have the average labor product, marginal labor product. But what we also did is we moved now from production to the cost. And so basically what we said is, in production we convert labor into output, call that Q, and then we have a typical S-shaped production function, which you see here also to the right, and we derived from here the average labor product, and the average labor product was somewhere here at this point of tangency. So that is the average labor product, and we had looked at the marginal labor product, had its maximum maybe here at that point of inflection, and the marginal looks maybe something like, here's the maximum, and it goes down like this. But then we moved to the cost function, and when it comes to cost, we convert output into cost. And here we assume we have only variable cost, so we forget about fixed cost for a moment. What we want to focus on is the shape, the curvature. And a typical cost function looks like this. So it's inversely S-shaped. So how do we get that? So I have here taken 10 values. For labor, actually 11, you know, when the labor output is 0, 1, 2, 3, 4, 5. And here I have picked up the respective output. So, and then the total variable cost is simply the wage rate, and every worker gets $10 or rupiah or euros. Okay, let's quickly copy that into another sheet, and then let's work there. Okay, let's get rid of the formatting. Let's make it maybe a little bit bigger. Okay, so now I want to replicate the cost function. For this purpose, I highlight the quantity, the output, and the total variable cost. And I don't need the star here actually. So it's our output, and in Excel, whenever you create a diagram from an array that you highlight, the first column goes on the x-axis. Okay, insert, recommended chart, and let's see. Oh, let's take this one, but let's remove. No, it's not a good one. Let's take the other one. Insert, recommended chart. Let's take this one. That looks nicer. It looks also more correct. Anyhow, what I didn't like is all those markers, but we can remove those. So let's format it a little bit nicer. Format axis. So I think the maximum is 100, so let's do that. Let's limit it to 10, and we don't really need those dots. So format data, series options, marker option, none. Okay. So you can see it looks a little bit like here on the left, and from there we would like to estimate the underlying curve. And what we cannot do is we cannot directly infer from this curve to the total variable cost function. It's mathematically really complicated. But what we can do is we can task Excel whether Excel could be so kind to estimate that function. And for this we have to use a trend line, and specifically a trend line which is polynomial, and polynomial of degree 3. So here we say 3. And then we say OK. And so now you can see that we have a line which fits the actual line pretty closely. And so this is a line of best fit, and maybe we can also add the equation on the chart. So now the next question is, if we use Excel to estimate the cost function, which one is it? Okay, so it is 0.0002x cubed minus 0.0241 x squared plus 1.743x plus 2.724. So the correct answer is D. Yeah, that looks correct. Okay, so we could work now with this one. That would be actually a very good line of best fit, but it's a little bit complicated. So what I did for the next question, I simplified it a little bit. I used this formula and made it look a little bit, make it a little bit easier. And we can just work with this one now. So maybe this one. So the green one is what we work with. And in order to show you that this is not a bad line of best fit, so what I do is I'll just show you what the estimated is, TVC estimated, which is now the one highlighted in green. So we just say equals to 0.1232 times Q cubed minus 0.03 times Q squared plus 2 times Q. So this is the estimated. And now let's take a look at how this one matches the real one. So TVC, that's the real one, and here we have the estimated. So recommend the chart. Now let's take this one here. And you can see it looks not too bad. Let's get rid again of all those dots and format those data series. Marker, none. And also for the other one, format data series, marker, none. Okay, you can see that it's good enough for our purposes. Well, let's do it like previously too. Let's format the axis to 100. Let's make the major interval 10. And yeah, we can limit the y-axis to 100 too. And we don't need a chart title. We know this is total cost. Okay, so now we can see it looks pretty okay. So we work with this one in the next couple of questions. And the question is, what is the average cost function? So in this case, the average cost function is average cost is total cost. We don't have fixed cost over Q, so that would be 0.002 Q squared minus 0.03 Q plus 2. Okay, 0.002 Q squared minus 0.03 Q plus 2, so it looks like C. Okay, what is the marginal cost function? So down the marginal cost function is so the marginal cost function is the first derivative of the cost function with respect to Q, and then we get 0.006. Oh, I forgot the 0. 0.06 Q squared minus 0.06 Q plus 2. So 0.006 minus 0.0 Q plus 2, so that looks like B. Okay, at what quantity does the average cost function have its minimum? Okay, so in this case what I want to do is, let's copy them. To the next page. So we have them here as well. Or I put them somewhere here. Okay. So here on top we have the average cost function. So at what, let's clean it up a little bit. So, and let's put the marginal cost function here to the left. Okay, at what quantity does the average cost function have its minimum? Okay, let's first draw it, because you can either calculate things by hand or just look it up in Excel. So let's first add to let's create another graph with the average cost, AC. And we said that is equal to 0.002 times Q squared minus 0.03 times Q plus 2. So that's the average cost, 0.002 Q squared minus 0.03 times Q plus 2, so that's it. Okay, let's copy this down. You can copy down, Control D. And the marginal cost, which is this one here to the left, is equal to 0.0006 times Q squared minus 0.06 times Q plus 2. Okay, so now let's take a look at it. But what we should expect is now something that looks like this. So we have marginal cost and average cost. And the marginal cost function should look something, like this. And the average total cost function should look something like this, which has its minimum where it intersects the marginal cost function. Okay, let's see if that's true. So we put again on the x-axis Q, and then we want to see what average cost and marginal cost look like. Insert recommended chart, all chart. Okay, that looks weird. There's maybe something wrong in the formula. Okay, let's double check the formula. Average cost 0.002 times Q squared minus 0.03 times Q plus 2. So insert recommended chart. Oh, that actually looks correct. What's wrong with the marginal cost? Marginal cost 0.0006 times Q squared minus 0.06. Actually, it looks all correct. So let's take a look at it again. Okay, let's double check. So average cost we said is 0. Let's do it again. Maybe I had a typo. Okay, equals 0.0002 times Q squared minus 0.03 times Q plus 2. Okay, let's copy this down. Oh, it looks different. There must have been a typo. The good thing is if you know what the functions are supposed to look like, you can actually tell whether you made a typo. Okay, the marginal cost is 0.1236 times Q minus 0.06 times Q plus 2. Okay, it looks like there's again a typo, 0.0006. Of course, I forgot the squared. B squared minus 0.06Q. Okay, so now it should look correct. Okay, I think that looks correct. So, okay, so now let's draw it, and I apologize for my mistakes. But sometimes you can also learn from mistakes. If something doesn't look right, the good thing is you can tell, oh, that doesn't look right, so you can go back and change it. But that's not an excuse, I didn't do the mistake on purpose. Okay, insert recommended chart now. Yeah, that is what we want. Okay, so we can put them actually underneath each other. So let's format the axes again the same. Tick marks. Okay, so we don't need the and okay, so now we have, you know, what looks like this here. And I remove again those marker options. here also. Okay, so now it looks pretty close to what we have here. And now let's go back to the questions. Okay, so at what quantity does the average cost function have its minimum? Okay, so the average cost function is 0.002 q squared. Just see that 0.000. Oh, okay, I forgot here was 0, that's why. Oh, there's another 0 here. So there was 3 zeros, 1, 2, 3. Okay, so that explains it. Okay, so where does the average cost function has its minimum? Well, it should be somewhere here where it intersects with the marginal cost function. So yeah, we have to calculate it. Okay, so we have to take the derivative dAc with respect to q. That has to be equal to 0. So we get 0.123 for q minus 0.03 equals 0, or 0.0004 q equals 0.03, then q star is 0.03 equals 0.03 divided by 0.1234, okay, 75. So yeah, we can't really tell it from hovering over because we don't really have here a very fine-tuned quantities. We have only, there's nothing close to 75. So when we can tell, 75 makes a lot of sense. Okay, so now we have to calculate that by hand, but the answer is 75. Okay, what is the value of the average cost in the minimum? So now we have to look up the y-axis value. Okay, so let's do that. And the average variable cost is 0.0002 times 75 squared minus 0.03 times 75 plus 2. There's certainly, again, another mistake, because it should be something close to 1 or 0.875. So let's see where we have made the mistake. Oh, here. 0.002 times 75 squared. It's actually 0.0004. Okay, so now I should have it right. 0.0004 no, it's 0.00275 squared minus 0.3 times 75 plus 2. So now it is correct. No, it's not. So average cost of 75 is 0. Oh, it's 1 0 too much here. Okay, so it's okay. But one has to be always careful So but if you applied this formula correctly and don't make any mistakes, you get 0.875. Okay, so, and what is the value of the marginal cost at the quantity where AC is minimum? Well, that is the same, because at the minimum we know that the minimum of average variable cost always intersects with the marginal cost. So that answer is also 0.875. And we could do the same thing if we calculated the intersection of those two, but that would be cumbersome, because we know that the minimum of the average total cost and the average variable cost is always where it intersects the marginal cost. Okay, so I'm sorry for some of the mistakes I made along the way, but yeah, sometimes you can learn from mistakes too. Not that I would produce mistakes on purpose, but I hope it is clear how to solve something like this. And in the next video we continue with working a little bit more with total cost function, and also the idea of perfect competition. But let's stop here and let's continue the next video.